It should have been a straightforward experiment. A wormhole had been created, stretching from lunar orbit to an empty region near Neptune, where a reception team was already waiting. Enormous effort and resources had been invested to reach into the quantum foam and extract a wormhole, a structure predicted by general relativity. Now it was here. This technology promised humanity the dream of interstellar travel. After final adjustments, the ship and its courageous crew entered the wormhole's opening, passing smoothly through the spherical portal. Observers watched the vessel shrink into the distance as it seemed to glide effortlessly toward its destination over 4 billion kilometers away. At the other end, the waiting party saw the ship slowly grow larger as minutes passed. An earlier probe had taken about 30 minutes to cross. The manned vessel appeared to be on a similar trajectory. But then concerns arose as the ship seemed to slow, then halt. It became motionless. 30 minutes elapsed with no emergence. Days turned to weeks, then months. Eventually, sensitive telescopes at both ends detected that the ship was still moving, but at an imperceptibly slow pace. Debates erupted over the next steps. Should a rescue mission be sent? Should the wormhole generator be shut down? Each option risked catastrophe, potentially disrupting the delicate balance of exotic forces stabilizing the wormhole and tearing the ship apart. The only safe choice was to wait, and so they waited. 500 years later, the remnants of the ship finally exited the wormhole. It was intact but barely functional, a battered shell after centuries of exposure to the harsh conditions within. The crew had long perished, their remains still secured in their seats. Finally, the wormhole was deactivated. Clearly, there had been a miscalculation. The predictions of general relativity alone were insufficient. They believed they had solved every aspect of the complex interplay between gravity and quantum mechanics, accounting for every possible interaction. Yet something had failed. Humanity gazed at the distant stars and felt profoundly alone. Wormholes are complex constructs. They emerge from the equations of general relativity, and the concept is nearly as old as the theory itself. But for those test pilots heading to Neptune, relativity is merely a tool that describes how gravity behaves in various scenarios. It does not dictate whether the universe permits those scenarios. So what would it take to construct a wormhole? What mechanisms might allow them, and which would forbid them? Could they transport us to dreamed-of destinations among the stars, or only to an early demise? Critics dismissed it as confusing, dense, and absurd. Yet to Edgar Allan Poe, it was his greatest achievement. It was 1848, just 1 year before his mysterious death. Having struggled financially as a writer for much of his life, his recent success with The Raven provided a welcome respite, which he used to compose what he considered his masterpiece, calling it the one great purpose of his literary life. The text is expansive, and today it receives little attention, especially compared to his more famous poems. However, some statements within its intricate passages stand out as oddly prescient. Roughly 2/3 through, in a section discussing the vastness of interstellar space, Poe declares almost out of nowhere that space and duration are one. In Poe's view, space and time were identical. Working nearly a century later, Albert Einstein had no idea he was, in a sense, echoing the thoughts of a long-dead New England poet. But that is precisely what occurred. It was 1905, a year that would become known as Einstein's Annus Mirabilis, his year of miracles. In that single year, Einstein published 5 papers, each with profound implications for our understanding of reality. One of those papers, perhaps his most significant, dealt with the relationship between motion and energy. In it, Einstein formulated his special theory of relativity, demonstrating that measurements of length and time are relative to the observer. But Einstein's former teacher, Hermann Minkowski, believed he hadn't gone far enough. Shortly after, Minkowski provided an intuitive geometric formulation of Einstein's work, presenting the universe as a 4-dimensional entity. Unlike Poe's ideas, however, this new spacetime did not mean space and time were identical. Instead, they were different facets of a single unified whole. Einstein learned from his teacher once more and quickly adopted this new concept, using it to make another monumental leap in human imagination. In 1915, Einstein introduced his general theory of relativity to an unsuspecting world. In the language of general relativity, spacetime is not static. It responds to the presence of matter and energy. The unified fabric of spacetime bends and warps under matter's influence, and in turn, that curvature guides the motion of matter. This process is happening all around you and within you right now. Ripples of gravity, known as gravitational waves, constantly wash over Earth, generated by distant cataclysmic events. As they pass, they deform space. If measured down to the scale of an atomic nucleus, you could feel yourself being gently stretched and squeezed by these passing waves. Much like Poe's writings, the theory of general relativity itself is beautiful, haunting, and sometimes complex and confusing. This is because general relativity is more than a simple physical theory of nature. It is a machine. You start with an input, a specific arrangement of matter. You feed it into the equations of relativity, and out comes an answer, a prediction for how that matter will behave under its own gravity. But general relativity does not tell you whether that arrangement of matter is real. It is up to you to decide what is possible and what is impossible. Indeed, relativity is not alone in physics in this regard. Newton's law of universal gravitation, which relativity superseded, operated similarly. You provide Newton with a material arrangement, and the equations describe how that system behaves. To get realistic answers, you must provide realistic scenarios. For example, you could theoretically calculate the gravitational influence of a solid metal rod 10,000 light-years long. It is up to you to decide if such rods exist in the universe. On that matter, Newton remains silent. But to complicate matters further, unlike Newton's laws, general relativity is not a simple equation taught in high school. Instead, it is a set of 10 equations in 4 dimensions, all interconnected and nonlinear. The physics community knew it was correct and useful, but it was so difficult to manage that most physicists preferred to focus on subatomic and astrophysical problems. The pioneering physicist J.J., nevertheless, progress was made soon after Einstein developed relativity. Karl Schwarzschild found a solution involving the simplest possible arrangement of matter while serving in the trenches of World War I. In this case, Schwarzschild took the machine of relativity and input something resembling the solar system. Out came a description of the strength of gravity around the sun. While intended to mimic the solar system, the solution contained something else. The possibility of a singularity. The idea was that if a ball of matter were compressed beyond a certain limit, it would continue collapsing, its gravitational pull so intense that it becomes a singular point of infinite density, surrounded by a one-way membrane called an event horizon. The machine of relativity had done its job. Now it was up to physicists to determine whether this result was possible. Most scoffed at the idea. Einstein himself rejected it. In a 1939 paper, he argued that no object could ever shrink to the point where gravity would overcome all other forces. Frozen stars, as they were called then, simply could not exist. But J. Robert Oppenheimer disagreed. Just months after Einstein's publication, Oppenheimer, working with his student Hartland Snyder, had just determined the maximum possible mass of a neutron star, the densest star type. He wondered what would happen if stars exceeded that mass limit. Oppenheimer and Snyder reached the exact opposite conclusion to Einstein. Incorporating the rest of known physics, they found nothing to stop the infinite gravitational collapse of a sufficiently massive star. From there, the machine of general relativity dictated exactly what would happen. Their paper stated clearly, the star thus tends to close itself off from any communication with a distant observer. However, on the very day their paper was published, Germany invaded Poland. Their work would be forgotten for decades, and Oppenheimer himself would be swept into the Manhattan Project and the ensuing political turmoil, never to return to astrophysical mysteries. Despite this, over time, it became indisputable. Black holes were real and possible. But was that all the machine of relativity predicted, or was there more? As Oppenheimer worked for the United States government, behind the Iron Curtain, Soviet astronomer Igor Novikov saw something else in the equations. The black hole had a twin. Novikov, born in 1935 in Moscow, quickly rose to leading positions at Moscow universities. Little is known about his personal life, except that working as a physicist in that environment was challenging. Research had to align with Soviet ideology. Scientists were often diverted to state-sponsored projects, and there was little hope of sharing work with the global scientific community. Yet Novikov had enough freedom to pursue unorthodox research lines. His great revelation in 1964 stemmed from a simple realization about gravity. Imagine filming someone tossing a ball into the air and catching it, but framing the shot so only the ball is visible, not the hand. If you played the video in reverse, would you notice? Both forward and backward playback would look identical, just a ball moving up and down. The mathematics of relativity are similar. They do not distinguish between processes moving forward or backward in time. Again, it is up to you to decide which is which. Gravity, including general relativity, does not care about time. A black hole is a specific solution to general relativity. In 1964, Novikov realized the equations for black holes could be run in reverse. Instead of trapping particles forever, they could eject particles forever. Instead of a black hole, it could be a white hole. Novikov proposed this idea to explain mysterious bright sources in astronomical surveys. But as he was in the Soviet Union behind the Iron Curtain, his work was largely ignored by Western scientists. White holes would be strange indeed, perhaps even stranger than black holes. They would still have singularities at their centers, but would be surrounded by the opposite of an event horizon, an anti-horizon. They would still possess mass, so you would be gravitationally attracted to one, but you could never enter. The anti-horizon forbids entry, just as a black hole's event horizon forbids exit. However, if you found yourself inside a white hole when it formed, you would not stay long. You would be propelled outward faster than light, like a flooding river you cannot resist, until you exited the white hole. The white hole would continue spewing matter and radiation until it was empty, leaving only a bare singularity and its anti-horizon. Stranger still, white holes could only have formed in the past and are now exploding outward, the exact time-reversed mirror of a black hole. Over time, physicists preferred a different explanation for those distant bright sources, energy emitted by matter falling into black holes. Yet as late as 2014, Novikov believed some might still be white holes formed by exotic mechanisms in the early universe and shining today. While most physicists dismissed white holes, a few were intrigued. Roger Penrose, who would later win a Nobel Prize for his work on black holes, learned of Novikov's work and thought it might explain another strange solution in general relativity. A tunnel from one universe to another. But it was Penrose's friend and colleague John Wheeler who gave these tunnels their modern name, wormholes. He discovered that white holes and black holes could be connected. In fact, the solution had been found decades earlier by a relatively unknown assistant of Einstein's. With that solution, Wheeler realized a small branch of relativity could blossom into a means to jump light years across the stars. He just needed to determine whether general relativity was producing genius or madness. About a dozen individuals from across Europe and North America, men and women, peered deeply into nature's inner workings. They devised ingenious mathematical proofs and derived results from groundbreaking experiments. They were, in a word, geniuses, but they all faced the same inescapable problem. They lived in the shadow of Albert Einstein. Like being the second-best swimmer next to Michael Phelps, Einstein's collaborators had no hope of claiming top prize as the smartest in the room. Yet Einstein did not disparage them. He frequently sought their help. He called one friend, Michel Besso, the best sounding board in Europe. One such working relationship also became personal, his first marriage. Then there was Nathan Rosen. He first met Einstein in 1934 at the Institute for Advanced Study, founded on Princeton's grounds a few years prior. Rosen was smart, capable, and hardworking. He had even proposed a largely correct model for the atomic nucleus before its discovery. But despite his intellect, his name would likely not be remembered today without his collaborations with Einstein. Rosen had been at Princeton for months before mustering the courage to meet the legendary physicist. When he timidly knocked on the door, Einstein was in deep conversation with another collaborator, mathematician Walter Mayer. But Einstein immediately put the young Rosen at ease. As Rosen recalled years later, he told Einstein about his work on solutions to the equations of unified field theories, and Einstein seemed interested, asking many questions. Soon, the three were engaged in a lively discussion of Einstein's current problems. This began a 3-year partnership. Officially, Rosen was Einstein's clerk, but their relationship resembled a friendship. Rosen was particularly interested in Einstein's efforts to unify gravity with electromagnetism, a pursuit most physicists dismissed as foolish, which likely strengthened their bond. During their time together, Rosen proposed a remarkable new outcome from the machine of relativity. At that time, Einstein was frustrated by singularities in his theories and by the trend of viewing subatomic particles as having no size or spatial extent. He sought to eliminate both problems, and Rosen found a way. Rosen and Einstein imagined following a line's path as it fell into a black hole and crossed the event horizon. Normally, this would be the end. The line crosses the horizon, is sealed off forever, and meets its fate at the central singularity. But Rosen suggested a radical idea. What if the line could keep going? What geometric construction would allow avoiding the singularity altogether? It was an intriguing question, and Rosen had the perfect machine to answer it: general relativity. Rosen found that following this path would lead back to the universe, but not to the starting point. The path would form a bridge between two different regions of the universe. There could be multiple paths, even shortcuts within spacetime. To complete their theory, Rosen and Einstein added electromagnetic fields to the calculations, hoping this solution, which eliminated singularities, could also explain subatomic particles' appearance and properties. In other words, they aimed to describe particles as bridges in spacetime. Unfortunately, the attempt failed. Thus, these Einstein-Rosen bridges, as they came to be known, faded into relative obscurity. Another 2 decades would pass before American physicist John Archibald Wheeler resurrected this obscure idea and gave the bridges a new name: wormholes. Wheeler had been curious since childhood. He never lost that curiosity or some childhood habits, like racing downstairs as fast as he could. This boundless energy led him to investigate questions others dared not explore, including the mysterious bridges of Rosen and Einstein. It was Wheeler who realized they might provide a mechanism for interstellar travel. The bridges were not mere mathematical constructs, but tunnels in spacetime that could be shortened. In principle, you could travel to distant stars with no more effort than a leisurely stroll or a race downstairs. But almost immediately after this revelation, he realized that attempting to travel through a wormhole would result in instant obliteration. Rosen and Einstein had imagined entering a black hole without meeting the singularity, emerging safely elsewhere. In this sense, the other end of their bridge was a white hole, the mirror image of a black hole. Wheeler, aware of Novikov's work in the Soviet Union, understood that nothing in general relativity's mathematics prevented such an eternal black hole, a spacetime tunnel with a black hole at one end and a white hole at the other. Problem solved? Not quite. These wormholes had 2 fatal flaws. First, general relativity is not the only physics theory. The universe involves more than pure gravity. Second, just because a wormhole can be created doesn't mean it will remain stable. For decades, physicists grappled with black holes and their vexing problems. Eventually, evidence prevailed, and now all physicists accept their reality. However, the same cannot be said for white holes. A white hole is a black hole run in reverse, possible in general relativity only because the theory does not care about time's flow. But we do, and so do other physics theories. The ironclad laws of thermodynamics, for example, care about time flow and entropy increase. You can collapse material to form a black hole, entropy increases, and all is well. But you cannot expand material to form a white hole. Entropy would have to decrease, which is strictly forbidden. there is no known mechanism to create a white hole from the materials and physics of our universe. When a star collapses, the rush of energies and forces prevents white hole formation, effectively pinching off that part of the Einstein-Rosen bridge, leaving only the black hole. Perhaps the early universe, rich with strange and unknown physics, could create white holes through exotic processes, leaving remnants in the modern universe. Could that be the solution? Unfortunately, no. Even if a white hole could be created through some arcane mechanism in the Big Bang or a laboratory, it could not last long. A white hole still has positive mass and a central singularity. If encountered, you would be gravitationally drawn toward it but could never enter. Its anti-horizon is the ultimate exclusive club, admitting nothing. You would be trapped, pulled infinitely closer to the anti-horizon, but never able to pass through. The energies involved would escalate uncontrollably and ultimately explode. Thus, no known mechanism can create a white hole, and once formed, none can keep it stable. For these reasons, physicists do not believe white holes exist in nature. Unlike their black hole twins, they remain mathematical flights of fancy within Einstein's relativity. But dreamers like Wheeler and Novikov are not constrained by a single theory. We have updated our understanding of gravity before and expect, or hope, to update general relativity in the future. So while current physics forbids white holes, perhaps a more nuanced approach could allow them, making wormholes possible. Yet even if magical technology could create a white hole and keep it open, turning it into the exit of an Einstein-Rosen bridge, you should never enter it. The problem is that the spacetime description by Einstein and Rosen, what we now call an eternal black hole, is static, a simple, frozen geometry. But as 4-year-old John Wheeler asked his mother, what happens when you go to the end of things? Wormhole interiors are not pleasant places. They are not serene tunnels through gentle spacetime. They are regions of intense, voracious gravity. Gravity can do more than pull inward, it can tear. The moon gently tears at Earth with each rotation, creating tides. An object falling into a black hole is stretched and thinned before being atomized, a process physicists call spaghettification. Gravitational forces inside a wormhole are so strong and tortured that if one formed, it would stretch along its length and compress across its middle, like an overstretched rubber band. Wormholes would rip themselves apart in a flurry of gravitational energy. Wheeler found this destructive process happens faster than light. Nothing, not even light, could travel through a wormhole's throat and emerge safely before the tunnel destroys itself. Briefly, you might glimpse your destination. Light from both ends could fall in. You could see the universe at your origin and endpoint. If someone entered from the opposite end, you could meet inside, share stories from across the universe, and then the wormhole would collapse, leaving you inside the black hole, with the singularity as your only destination. You would die. After Wheeler's pronouncement on wormholes' finality, most physicists accepted they were literal dead ends. Once you cross a black hole's event horizon, whether as a single entity or a wormhole entrance, you cannot escape. No clever geometric trick by Einstein and Rosen could save you, but predictably, that wasn't the end. Decades later, a third generation of physicists took up the challenge posed by Einstein, Rosen, and Wheeler. In fact, one of Wheeler's own students found a way to create a stable, traversable wormhole. He just needed a little help from science fiction. If you seek good physics in science fiction, movies like Star Wars are not the best source. Laser beams traveling slower than real bullets, moon-sized space stations defying gravity, planet-obliterating weapons, and spaceships that travel faster than light with a switch flick. While entertaining, they lack grounding in known physics. But sometimes a writer or director aims to align more closely with our understanding of the universe. Its world is recognizable, with a crop-destroying disease representing climate change and a diminished NASA organizing a mission to explore a mysterious object in the outer solar system. Despite this realism, Nolan wanted his astronauts to travel vast distances quickly. He enlisted physicist Kip Thorne, an expert in general relativity and Nobel laureate, for ideas. Thorne recounts that Nolan considered faster-than-light travel non-negotiable initially, but after in-depth discussions, he conceded. Faster-than-light travel was out for Thorne. Instead of refusing Nolan, he compromised and suggested a possible solution: a wormhole, a shortcut through spacetime that was stable and traversable. While fantastical, it wasn't entirely ruled out by modern physics. In Sagan's story, humanity receives instructions to build a wormhole, and a team travels through it. In one dialogue exchange, Sagan wanted characters to muse on how it might be possible, but didn't know what they should say. So, like Nolan later, he turned to Thorne. By then, wormholes were known to be catastrophically unstable. Thorne and his collaborators devised a way to stabilize them. For Thorne, this was business as usual. It was clear that the wormholes of Rosen, Einstein, and Wheeler didn't work. White holes aren't stable, assuming they can be made at all, and the bridges they form with black holes are only temporary. To make a wormhole useful, or traversable, in Thorne's jargon, two problems must be solved simultaneously. First, the wormhole's entrance must be placed outside the black hole's event horizon to avoid doom at the singularity. Second, the passage itself must be stabilized, exerting pressure on the walls to prevent instant collapse. Thorne found one simple cosmic trick within general relativity's equations that could solve both problems. Typically, physicists use general relativity in one direction. Given an arrangement of matter and energy, they calculate the resulting spacetime curvature, then gravitational forces and future behavior. But Thorne worked the equations in reverse. He started with a specific spacetime structure, a wormhole bridge between two universe regions, and asked what configuration of matter and energy was required to make that tunnel stable. Oblivious to what is possible in the real universe, the machine of relativity obliged and produced an answer: negative mass. Not antimatter, which has positive mass but opposite charge but negative mass. A football weighing negative 500 grams, a cut of meat weighing negative 2 kilograms. Negative mass does not pull and attract, it pushes and repels. If fashioned into a shell, space-time around it responds by pushing itself apart. This pressure can inflate a wormhole's entrance beyond the event horizon, allowing entry without being swallowed by the central black hole. The same negative mass pressure keeps the tunnel open, resisting its natural inclination to tear apart and permitting objects, light, particles, and spaceships to travel through. There it was, the key to a working wormhole revealed in the cold mathematics of relativity. There was one problem: where could we find negative mass? Despite decades of searches and experiments, physicists and astronomers have found no sign of matter with negative mass, dubbed exotic matter. Even if it existed, it would pose severe problems for our most fundamental concepts of momentum and energy. Exotic matter might behave oppositely in response to forces. Kick a negative mass football, and it flies backward, not forward. Drop it, and it soars upward. Exotic matter would violate momentum conservation, a foundational principle behind almost every modern physics theory. Of course, momentum conservation could be wrong or inadequate, but after centuries of investigation, it has shown no weakness. Thus, exotic matter seems a dead end. But Einstein showed that matter and energy are two sides of the same coin. So if exotic matter cannot be made, perhaps exotic energy could suffice. Exotic energy's origins trace to an old-fashioned shootout. Just after World War II, the streets of Copenhagen stood in for dusty Old West thoroughfares. Suit-wearing cowboys wielded mock weapons and engaged in simulated duels. One could draw whenever they chose, the other had to wait for their opponent's move. One participant was Hendrik Casimir, a graduate student more interested in particle physics than fake gunfights. Overseeing this odd experiment with stopwatch and notebook was Niels Bohr, the godfather of quantum physics. Casimir was in Copenhagen to study quantum mechanics, but Bohr diverted him to test a hypothesis called the gunslinger effect, the idea that automatic responses are faster than intentional ones. Reluctantly, Casimir took a break from his studies to play gunfighter. Perhaps that image of graduate students staring each other down, pretend guns at the hip, stayed with him as he returned to physics and imagined the tension between two metal plates held a small distance apart. Studying quantum mechanics under Bohr, his calculations revealed a remarkable property. With nothing between two metal plates, they would spontaneously move toward each other, as if drawn by an invisible force. This turned out not to be a new force of nature, but an artifact of quantum mechanics. Quantum mechanics does not envision a universe full of particles, but fields occupying all spacetime. These fields are everywhere, filled with vibrations constantly flickering in and out of existence. Sometimes these vibrations gain substance and travel, what we call a particle, but most vanish before the cosmos notices. Infinitely many vibrations occur throughout the universe. However, between the plates, these vibrations are restricted. Through careful calculations, Casimir showed that the difference in vibrations outside and inside the plates creates a gentle push, a force compelling the plates together. Since the region inside the plates has less energy than the vacuum average, the Casimir effect, named in his honor, is an expression of negative energy. A sufficient concentration of negative energy could hold open a wormhole, stabilize it, and allow traversal. Such a wormhole would be wondrous, unlike anything else observed. Its entrance would be a sphere resembling a black hole's event horizon, allowing entry from any direction. But it would blaze with light, not from surrounding stars, but from a distant part of the universe filtered through the opposite end. You could wave to a friend in the Andromeda galaxy, examine its stellar contents, and travel there yourself. Movement through this wormhole would be relatively stress-free, assuming the tunnel was properly stabilized with adequate negative energy. You would experience no strong tidal distortions or extreme gravitational warping, though your view of the outside universe would be highly distorted due to the wormhole's unique geometry. You would pass through unscathed, skipping tens, hundreds, millions of light years without a hitch, at least in principle. Yet again, things are not so straightforward. We have laws of physics like general relativity, but the math within these laws often has broader scope than our physical universe. Some solutions, like black holes, are permitted, others, like white holes, are not. To navigate this, physicists have developed rules called energy conditions to guide which solutions are allowed. There are various conditions, strong, dominant, weak, generally dictating how energy can behave. For example, energy cannot travel faster than light, just like matter. Another condition states that local mass cannot be negative. Exotic matter is forbidden due to momentum implications. Yet another says local gravity must always be attractive. There may be repulsion, as seen with the universe's accelerated expansion, but not at small scales. The Casimir effect violates the weak energy condition, the rule that energy must always be positive, but this is only true in the hyperlocal space between the plates. Averaged over a larger volume, including the plates and surroundings, total energy is positive, restoring the condition. Whether any energy conditions can be violated at large scales remains an open question. They seem to hold based on our gravity experience, but they are only guesses. Perhaps strange quantum oddities like the Casimir effect could be amplified by a sufficiently advanced civilization. Indeed, quantum theory predicts countless, even infinite, wormholes. The same quantum fields that constantly vibrate give rise to an invisible sea of particles disrupting spacetime at the tiniest scales, the quantum foam, a roiling sea of broken spacetime operating at scales so small they escape notice. That foam contains countless submicroscopic wormholes. Perhaps, as Thorne mused in his 1988 paper, an advanced civilization could pluck one from the quantum foam and enlarge it to macroscopic proportions. Maybe they could violate energy conditions at large scales, allowing a Casimir-like effect to span intergalactic lengths. And perhaps that civilization could use this technology to enable a brave crew to travel to distant stars. But a functioning wormhole, as tantalizing as it sounds, is more than a bridge to faraway galaxies. It is also a tunnel into the past. You receive an invitation to a party at the University of Cambridge, 7E. The party occurs precisely at 12 noon Universal Time on June 28, 2009. There will be champagne, and your host is famed astrophysicist Stephen Hawking. At that precise place and time, Hawking arrived at the reserved room, sipped champagne, and waited. After several hours with no guests, he left. Only then, after the party concluded, did he distribute his invitations. It was a party for time travelers. The lack of guests seemed reasonable experimental evidence that time travel was impossible. After all, who in the distant future would decline an opportunity to meet Stephen Hawking? But Hawking was not entirely dissuaded. He hoped copies of the invitation would survive for thousands of years. Maybe someday someone in the future would find the information and use a wormhole time machine to attend his party, proving time travel possible someday. So was he correct? Could wormholes enable time travel? As far as we observe, time travel to the past is impossible. Yet once again, the machine of relativity seems to allow it. Assume our physics knowledge advances, and we discover how to violate energy conditions, constructing a working, traversable wormhole held open by exotic matter or negative energy. You build your device and bounce between stars faster than light, never locally exceeding light speed, in accordance with relativity. Yet you arrive at your destination before news of your departure reaches it. Then you take one end of your wormhole and accelerate it to nearly light speed. It doesn't matter where you take it, speed is key. Due to special relativity, that end experiences time dilation, its clock unsynchronized with the other end. If you travel outside the wormhole back to the non-accelerated end and journey through, and your outside travel time is less than the time difference between the two ends, you can arrive before you leave. Wormholes are not just shortcuts in space, they are shortcuts through time. If the universe allows wormholes, it automatically allows time machines. But time travel opens so many paradoxes that most physicists consider this sufficient evidence that wormholes are impossible. Why can't we travel through time? Consider this: you have a machine that creates a wormhole. You can turn it on and off. You turn it on, travel into the past, then turn it off or destroy the machine entirely. But if the wormhole is off or destroyed, how could you travel into the past to deactivate it? This is just one of many paradoxes inherent to time travel. Thus, anyone deeply studying wormholes must confront time travel's difficulties and devise solutions. Novikov himself, the father of white holes, proposed the self-consistency principle. He suggested time travel might be allowed, but only in limited cases where the past remains unchanged. For example, you throw an asteroid toward a wormhole entrance. At the last moment, another asteroid knocks yours off course. It still enters the wormhole, but at an unexpected trajectory. The asteroid travels through and emerges in its own past, colliding with itself just before entry. Thus, the universe's history remains consistent. The past is unchanged. Some unknown mechanism prevents alteration. Other physicists rejected time travel altogether. Hawking's chronology protection conjecture flatly forbids time travel. Instead of trying to allow wormholes and time travel, we should use the apparent prohibition as a guide to building an improved theory of quantum gravity. Yet that is not quite the end. Perhaps wormholes are not tunnels into the past, but bridges to entirely different universes. In the many worlds interpretation of quantum mechanics, espoused by Hugh Everett, every quantum interaction leads to a branching multiverse. For example, an experiment with a 50-50 chance yields one universe where one outcome is measured, and another universe where the other is measured. This interpretation has flaws, but is not definitively ruled out by experiment. It opens the possibility that wormholes could allow travel to other branches of the infinitely expanding quantum tree. Following this logic, perhaps there is a universe where revelers from the future attended Hawking's party. In their universe, Hawking's party was always a success. In ours, always a failure. Hawking's chronology protection conjecture holds, and time travel is still allowed. Thus, wormholes in general relativity's equations open a range of intriguing possibilities, leapfrogging among stars, jumping into our own pasts. Perhaps wormholes are forbidden by yet unknown gravity laws. Perhaps they are allowed but contain hidden flaws and traps, or perhaps they are just too slow. In 2019, researchers at Harvard University and the Institute for Advanced Study, where Rosen met Einstein nearly a century before, found a way to concoct wormholes without exotic energy. But there was a catch. These wormholes took much longer than expected. They weren't working with a gravity model applicable to our universe, but a special spacetime with only 2 spatial dimensions and 1 of time. Surprisingly, this wormhole required no exotic matter to stabilize it. Gravity itself assumed a repulsive character in the extreme wormhole geometry, enough to hold it open and allow passage. But analysis revealed such a tunnel could not be used to skip around the universe faster than light. Paths through the wormhole were even slower and longer than paths through flat space. Not only was this wormhole a poor way to traverse the cosmos, it was worse than not building one at all. Admittedly, the researchers used a modified spacetime structure not identical to our physical universe, but it leads to the intriguing, if frustrating, idea that wormholes may be possible, yet useless. Despite recent discoveries, the current consensus among most physicists is that wormholes are ultimately not allowed, but they can still serve as useful playgrounds to test new ideas in gravity and quantum mechanics, to study physics in extreme configurations, and to use their strange behaviors as probes into corners of knowledge hidden from us. If you enjoyed this journey through the cosmos, please show your support by liking this video and subscribing to the channel. Your engagement helps us continue exploring the universe's greatest mysteries. Share your thoughts in the comments below. We'd love to hear what you found most fascinating. Thank you for watching, and we look forward to seeing you next timer to stabilize it. Gravity itself assumed a repulsive character in the extreme wormhole geometry, enough to hold it open and allow passage. But analysis revealed such a tunnel could not be used to skip around the universe faster than light. Paths through the wormhole were even slower and longer than paths through flat space. Not only was this wormhole a poor way to traverse the cosmos, it was worse than not building one at all. Admittedly, the researchers used a modified spacetime structure not identical to our physical universe, but it leads to the intriguing, if frustrating, idea that wormholes may be possible, yet useless. As Stephen Hawking reflected on the difficulties of understanding wormholes, time travel, and quantum gravity, not only does God play dice, but he sometimes throws them where they cannot be seen. If you enjoyed this journey through the cosmos, please show your support by liking this video and subscribing to the channel. Your engagement helps us continue exploring the universe's greatest mysteries. Share your thoughts in the comments below. We'd love to hear what you found most fascinating. Thank you for watching, and we look forward to seeing you next time.